All right, lesson 6 is on area scale factor. So just to review, we previously covered linear scale factor, right? When our dimensions changed. Let me just change this solid, let's make this black. So if you recall, when we wanted to find the new image, how its size or length or width it was, we multiplied it by its scale factor. Well, now we're going to look at a two-dimensional scale factor. So I'm just going to choose a different color, maybe this color here. So just to review this chart, and we're going to use this chart in our lesson. We have our linear scale factor, which is often just called scale factor. So if it says find the scale factor, it doesn't say which type, and we always know that's linear. Then we have area scale factor, and we have volume scale factor. So far we've only covered the first one, and often we give it the symbol K, and we find it by taking our new dimension, so new length, new width, right? New radius, dimension, over our original dimension. And remember, we can spot it because the units are linear, or they're one dimension. So like centimeters are the units, feet, meters, and so forth. And so it's one dimensional. So that's linear scale factor. Today we're going to cover linear scale factor. And how do we get linear scale factor? Well, area scale factor is often known as K squared. So we can get it by taking our linear scale factor and squaring it. So if my linear scale factor was 2, then our area scale factor would be 4. Okay, because we have to increase both those dimensions by 2, and then 2 times 2 is 4. So we also can find it with taking our new area, if we had the area of the new shape, and divide it by our original area. It would also give us our area scale factor. And so one way we can figure out our area scale factor is if the units are two-dimensional, so centimeters squared, feet squared, meters squared, and so forth. And so that's going to give us, it's a two-dimensional unit. And then volume, we're going to look at that tomorrow, and that's by taking our scale factor and our linear scale factor and cubing it. Let's use something like pink. So it would be K cubed, or linear scale factor cubed. We can also find it by taking our new volume and divide it by our original volume, and that's our volume scale factor. We know we're working with volume when our units are cubics, so it's three-dimensional. So centimeters cubed, feet cubed, meters cubed, and so forth, etc. Okay, so let's look at our very first example, and we're going to investigate. So here's a problem. We're investigating the relationship between linear scale factor and area scale factor. So we have a rectangle. So the first rectangle they gave us was 3 by 5, and let's go through a new one with 9 by 6. So we have a rectangle that's 9 by 6 centimeters. Okay? So it says, what's the original area? Well, we take 9 and we times it by 6, because area is length times width. And so 9 times 6 is 54. So 54 centimeters squared. Now our scale factor is 1 to 3. So remember, as a fraction, we take our new divided by original, so 1/3. And how do we get our new, and this is a linear scale factor, so that means it's affecting each dimension individually. So how do we get our new dimensions? Well, grab your calculator. We want to take our original dimension and times it by our linear scale factor. Come on, there you go. So our original dimension, one of them was 9 centimeters, times it by our scale factor, and our scale factor is 1/3. That would be our scale factor, 1/3. So 9 times 1/3 gives you 3. So one of the sides is 3 by, okay, the other one was 6. So 6 times the scale factor is 1/3, and it's 2. So 3 by 2. So our new shape is 3 by 2. So what's our new area? Well, our new area would be 3 times 2, length times width, because this was our initial length, width. Our new length and width, 3 times 2 gives you 6. And so let's find our area scale factor. How much was the area increased by or decreased by? Well, our new area was 6, and our original was 54. So let's grab our calculators and reduce that. 6 divided by 54, and math, enter, enter, is 1 over 9. So 1 over 9. Okay, so notice our original was 1/3, our new is, so that's how much every dimension was basically divided by 3, right? It's 3 times smaller. And so 1/3 was our linear scale factor. Our area scale factor is 1/9. Let's look at another one. So now our rectangle is 4 by 8. 4 by 8, length and width. So our new area, 8 times 4, gives you 32. Our scale we're going to use is a 3 to 2 scale. So we want to make a new object that's a 3 to 2 scale. So here's our new original. It's like new over original. 3 over 2 is our scale factor. So if we want to find our new dimensions, and these are the linear scale factor, we take our old dimension. So one of them was 4. I'm going to multiply it by my scale factor. So the 4 became a 6. So 6 by, and the 8 became, so 8 times 3 over 2, 12. So 6 times 12 will give us our new area. 6 times 12 is 72. So let's find our area scale factor. Our new area is 72. Our original is 32. So let's divide these. Let's grab your calculator. 72 over 32. Math, enter, enter, gives you 9 over 4. So again, notice how we had a scale factor, a linear scale factor of 3 over 2, and now we have 9 over 4. Let's look at one more example. We have a 3 by 12, so length 3, width, or actually length 12, width 3. So area, 12 times 3 gives you what? 12 times 3 is 36. Now, we want to take our dimensions and change them by a scale factor of 2/3. So I'm going to take the first dimension, which is 3, multiply it by 2/3, and I get a dimension of 2 by 12. We're going to take and multiply it by 2/3, and it's 8. So our new area, 2 times 8, is 16. So new area was 16, old area was 36. So what's our area scale factor? 16 over 36, math, enter, enter, 4 over 9. So notice the correlation, right? Our scale factor was 2/3, our area scale factor 4 over 9. So what would be an easy way to just skip all figuring out the area and go from our scale factor to area scale factor for each one of these? And if you noticed, they're squared, right? Our area scale factor squared is equal to, our linear scale factor squared is equal to our area scale factor, right? So that is like for sure study sheet material. We square our linear scale factor, we'll get our area scale factor. So let's look at some problems. And one thing that I recommend is that when you set up a problem, you might want to make a chart, because there's different types of scale factors and you don't know which one they're going to give you. And they might give you one, but you'll need another. So we have our linear, which is like our K. Then we have our area and our volume. And I know we're not using volume today, but get in the habit of writing it. So there's my little chart. So we can write down our scale factors if they give them one. So here it says, Maggie has scanned an 8 by 10 photograph to her computer. Maggie would like to increase the size or the area, specifically the area, so we know we're dealing with area scale factor, by 44%. Determine the area scale factor and linear scale factor. Okay, so she wants to increase our area by 44%. We don't want to use just 44% as our scale factor, because that would be decreasing it. For increasing it by 44 means we're starting with the 100 and we're adding the 44%. So that we have 100% plus the 44 if we're increasing it. If we are decreasing it, we would subtract it by 44. And so our area scale factor is 144%. Now let's get it out of a percent though. So if our area scale factor equals 144%, let's change it to a decimal. Remember, if we want to change a percent to a decimal, we just take the percent and divide it by 100, and then you have your number, 1.44. So that's my area scale factor, 1.44. So I'm going to fit it in to our chart. So we know that our area is 1.44. So how do we get our linear scale factor? We're going to go backwards. So notice when we wanted to go forward, if I knew my linear, to get my area, I would square it. So to go backwards and get our linear scale factor, we need to square root it. So if I wanted to go this way, I'd have to square root to get to my linear. Square root it. Okay, so our linear scale factor is going to be the square root of 1.44. So grab your calculator. The square root, our area scale factor, and it's 1.2. 1.2. So it makes sense. If linear was 1.2 and I squared 1.2, that's how we'd get our area scale factor, 1.44. So to go backwards, we square root it. So that means each dimension we would multiply by 1.2, or if we had the original area, we'd multiply that by 1.44 to get the new area. So explain why these scale factors are different. Well, the reason why is because the area is the square of the linear scale factor. The area scale factor is the square of the linear scale factor. Remember we drew that picture before, that if I had, say, a little square, and I double its length, so each dimension I double. So I'm going to now make this side twice as long and this side twice as long. Well, then how many of those original square areas would fit into it? And it would always be, so if we doubled the length, we now have 4 times the area. There's 4 squares. So if we doubled each one of them, it's going to be 4 times. So this guy's a 1 by 1, and 2 by 2 would give you an area of 4 compared to the 1. So it'd be 4 times the area. I should use blue. Makes it look better. Right? It'd be 4 times. If we took that original dimension and we doubled it, so this by this, and we doubled its length and width, then the area would be 4 times. Okay, so determine the dimensions. So dimensions are always talking about a linear measurement. If you see the word dimensions of the enlarged photograph. So if they're talking about the dimensions, then we want to change the 8 and change the 10, the 8 by 10 photograph. And if we're dealing with dimensions, that's a linear measurement, so we're going to multiply it by the linear scale factor. So each one of these, I'm going to multiply by my 1.2, my linear scale factor. Because linear measurement, you're going to use a linear scale factor. If you're dealing with an area measurement, area scale factor. Okay, so 8 by 10, where each of them are going to multiply by 1.2. So 8 times 1.2 and 10 times 1.2. So 9.6 and 12. 9.6 and 12. So our new dimensions are 9.6 by, 12. It was a 12. There's our answer. The enlarged photograph will be printed at a digital print shop and on a color printer. Assuming the white areas of the photograph will also use ink, calculate the area the printer must cover by the following 2 methods. So first method, using the dimensions of the enlargement. So remember we already found our new dimensions. So it'd be 9.6 centimeters, is inches, by 12 inches. So we could just find our new area that way. 9.6 times 12. So that's one way we had our new dimensions. So 115.2 inches squared. So squared units. Another way we could have got our new area is take our old area and multiply it by the area scale factor. So the original area area original was an 8 by 10. 8 by 10. So that would be 80 inches squared. So our new area we could get by taking our original area and multiplying it by our area scale factor. So because we're working with the area units, we have to use the area scale factor of 1.44. So that means that the area is 1.44 times larger. So 80 times 1.44 gives you 115.2. So it should be the same answer. There's just two methods we can use to get to it. One of them we used our linear measurements and linear scale factor. Here we used our area and area scale factor. And they result in the same answer in the end. And so when you're looking for new area, you can get your new area by taking your area scale factor multiplied by original scale. So original area times area scale factor. So new area is original area by times area scale factor, just like the new dimension was equal to the original dimension times the linear scale factor. All right, turn to the next page. Page 42. So Maggie also produces a print whose area will be reduced by 25%. So if it's reduced by 25%, we have our original 100%. We want to take away 25%. That means we have 75% remaining. So what would be my area scale factor? Because it's the area that we want to change. We want the area to be reduced. Our area scale factor would then be 75%, or as a decimal, 0.75. Because we only want 75% of the original. So remember I showed you make that chart. So we have our area scale, or our linear scale factor, area scale factor, and volume scale factor. I should say linear. Okay. And remember, here's k squared, k cubed. So they give us our area, which is 0.75. It says determine the dimensions. Whenever you hear the dimensions, you should be thinking we're dealing with a linear measurement. I need my linear scale factor. Okay, dimensions are always linear. So dimensions, if you see the word dimension, we're dealing with linear, meaning I'm going to need my linear scale factor. So how do we go backwards? We know to get to area, we'd have to square our linear measurement. If we have our area scale factor, then we need to square root it. So our let me just adjust my mic, sorry. Our linear scale factor is a square root of our area scale factor, and that's always true. So square root of 0.75, let's type that in. Square root of 0.75. That gives us not the nicest number, but that's okay. It's approximately, we can just store that number and use it. I can store it as x, for example. So it's approximately 0.866. I might just use square root of 0.75. So approximately 0.866 rounded. Okay, so that's my linear scale factor. Remember, our original dimensions were 8 by 10. So to get my new measurement, it was 8 inches times our linear scale factor, which is about 0.866. We could also just multiply it by the square root of 0.75 if you want an exact. And then also the 10 inches. So you could use, honestly, if you use 0.866, because we're rounding to the nearest hundredth, it should be fine, right? So notice if I took 8 and multiplied it by 0.866, versus if I took 8 and multiplied by square root of 0.75, it's still to the nearest hundredth going to give you the same answer, because we want 2 decimal places. So if you just want to use 3 decimal places here, it won't mess up our final answer. So 6.93, and then the 10 inches times the linear scale factor. So we can use square root of 0.75, or we can use 0.866, and it's 8.66. So our new dimensions are 6.93 inches by 8.66 inches. And that would give us a diagram that the area is 75% of the original, so 25% less. There you go. Okay, example 2. Marco, owner of a Map-It Incorporated, has produced a map of Canada with his employees. The area of the province of Alberta is approximately 661,850 kilometers squared. So they give us an area. How do I also know that? Because the units are squared. On Marco's map, the area of Alberta is represented as 264.74 centimeters squared. The scale of the map, or the linear scale factor, can be written in the form of 1 to x. Calculate the value of x to the nearest whole number. So let's just kind of start by making a little chart. So we have our linear scale factor, our area, and our volume. Now obviously we're not going to be dealing with volume in this question. It wants our linear scale factor. So in order to do that, it gives us area information. So we have to start by figuring out our area scale factor because we're given area units. And then we can go backwards to get our linear scale factor. So remember, on that very first slide here, to get another way we can get area scale factor is take our new area and divide it by our original area. And we can do that because they give us our map, 2 different areas. So let's figure out which ones are new and which ones are original. Go back, there you go. So the area of the province is that much, that's the actual area. And then the map, so we're comparing the map to the original. And we can also use this as a hint, right? It's 1 to something. And so this is obviously larger, so small to big. And our small one is the 264.7. That's our new, that's our map compared to the original or the actual. So when we find now these aren't the same units, but that's okay for now. Centimeters squared compared to 661,850 kilometers squared. And that's going to give us our area scale factor. So our new over our original, or our actual. So let's divide that and see what it gives us right now. 264.74 divided by 661,850. Let's see if it actually gives us a number. And go math, enter, enter. Here's a problem, right? It's not reducing the fraction for us. So I'm actually going to flip our fraction to see if that this guy will divide into the other, the other way around, and see if we can get 1 over a number. Divided by 264.74. So it actually will go into it exactly 2,500 times. And so this should be 1 over 2,500. 1 centimeter squared is equivalent to 2,500 kilometers squared. Okay, so now that we know that's our scale factor for area. So how do we go, if this is our area, or a k squared, or linear squared, how do we go backwards again? We square root. So our linear scale factor, we're going to square root our area. Square root of the 1 centimeter squared over 2,500 kilometers squared. So square root that. So square root 1 over 2,500. And what happens is when we square root our squared units, they're going to become linear units. So change that to a fraction is 1 over 50. So 1 centimeter is 50 kilometers. So we're almost there because we have 1 to 50. But right now, this is a ratio. What do we know about ratio? Oops. Let's read that properly. What do we know about ratios versus rates? Remember, ratios have the same units. So right now we have 1 centimeter is equivalent to 50 kilometers. That is not a ratio. That is a rate. So we need them as the same units. So the 1 is okay. We want to change the other guy. So we need to change 50 kilometers into centimeters. So I'll write this really slow, low down below. And it's king Henry's daughter Mary died chasing men. So we're going from kilometers to centimeters. That means we want to go 1, 2, 3, 4, 5 to the right. So 5 decimals to the right means we're adding 5 zeros. So 1 centimeter is 5, 0, and then add 5 other zeros. So 1, 2, 3, 4, 5 other zeros. And so there's our ratio. 1 to 5 million is our solution. So that's the linear measurement, 1 to 5 million. So x is 5 million. Okay, now it's very important that when we convert units, we have to make sure they're linear units to convert them. We haven't been taught yet how to convert an area unit to an area unit. It's very different than converting linear units. So if you have to convert units, you have to change it to a linear scale factor first and then convert the unit. Okay, so on the map, I'm just going to write 1 over 50 just in case we need that later. That was our linear scale factor. On the same map, the area of the province of British Columbia represents this many centimeters. Now, one thing I actually should add on my little chart is 1 centimeter squared was 2,500 kilometers squared. And 1 centimeter is exactly 50 kilometers. Because it was a rate and not a ratio. So here they give us, okay, a map diagram of 576.839 centimeters squared. So there's a few ways we can do this, solve this problem. One way is we can set up a ratio. We know 1 centimeter squared is equivalent to 250 or 2,500 kilometers squared on the map. And they give us the map, 376.839 centimeters squared, and we're looking for x kilometers squared. That's a really easy way to set it up. This way you know you won't mix up, do I divide, do I multiply by 2,500 or 1 over 2,500? So, I mean, there you can see your units match up, and then we just cross multiply. So 1 times x is x, and then 2,500 times the 376. And notice we had to use our area scale factor because our units are area. And there it is. So 942,097.5 kilometers squared. So that's one way you could have solved that problem. It says it round to the nearest 100 square kilometers. So 100 place values right at the 0. The 9 is going to round that to a 1. So 942,100 kilometers squared, approximately, is the area of British Columbia. Now, you could have also done using unit analysis. So we know we have 376.839 centimeters squared times, now we're going from the map to the original instead of from the original to the map. So in this case, we want centimeters squared to cancel out, and we're looking for kilometers squared. So unit analysis, and then we fill in that ratio. So remember, 1 centimeter squared was 2,500 kilometers squared. This way, the centimeters squared cancels out, and it gives us that same value. So that's using unit analysis. So put around 942,100 kilometers squared is the area of BC. Probably have a sentence when we have a word problem. Okay, so the assignment is 1 to 8 here. And I think we can omit, I think it's all good. Just double checking it. Yeah, so 1 to 8 is the assignment, and that's the lesson.